Thank you very much, and good afternoon, everybody. I'm going to be presenting some work in progress, really. It's what I don't actually have any sort of specific outcomes at the moment at a high level to present. So what I'm really going to be doing is presenting methodology and some intermediate outputs from what I've been doing. So it's more about the sort of analytical processes, analytical methods that we've been using. And really, when I'm talking about development of strategic investment models, obviously for that reason, I'm really focusing on the development of deterioration models for carriageways. We'll be working on other asset types as well in future, but at the moment I've really got some results for carriageways. And also I'll just add as well that by strategic investment models, I mean we're really talking about 10 to 20 years network level models rather than individual stretches of road, although I will sort of give some indication as to how those models might be used, say, for prioritisation of shorter term programmes, so forward work programmes. Just to quickly place us on the map, this is Stockport in the red boundary. This is northwest England. Sorry for those of you who might not be familiar with the geography. So Liverpool's over on the Irish Sea coast over there. We're on the southeast. I should yes, use the pointer. The southeast corner of the Manchester conurbation with the Peak District National Park there, which we border onto. So actually the east side of the borough is largely rural, but that said, we've actually got about 90% of our road network is urban. And it's still a fairly small network though. It's about 945 kilometres. I'll just quickly go through the main messages really, because we'll be sort of covering an awful lot of different bits of detail going on, but I thought if I try and pick out the main messages to start off with. I hope to be able to demonstrate a methodology for developing deterioration models. It maximises the use of local data, stuff that we've already got, but perhaps without requiring the levels of data collection really at the start, that, say, some mainstream models, thinking of perhaps, say, HDM4, might require before you can even get started. We really sort of looked at how we could make the best use of the data we had already. And also that particularly, I guess, in urban networks where we've got an awful lot of things going on with reinstatements, the variance in highway performance is also particularly important, and we need the models to be able to account for that. Particularly again because we may not be able to invest as much in detailed data collection as other larger authorities would be. At a more strategic level, it's really about trying to start a continual learning process about our assets, because we are facing a lot of unknowns, commodity price instability, aging infrastructure and climate change. So I mentioned a little bit about how we deal with that, well, how we might be looking at that in future. Estimating failure and transition probability curves, and then estimating the effects of road variables on transition probabilities. I'll actually talk about those as separate things because the method I'm talking about, ideally you do them both together, but when you've got limited data, you can actually do these as separate processes with the models that I'm about to talk about. Right. So the objectives of the investment model, fairly straightforward. So identify a preferred long-term option for investment in highways maintenance in Stockport Borough. And to test alternative scenarios then and coping strategies, which is particularly important because we start off on the back foot at the moment with the current financial situation. Our finance department really sort of put the initial impetus into this. And their questions were not about increasing investment. So we need to try and start from that point and turn it round to looking at increasing investment. They're really interested in other capital priorities as well, how we balance that against schools and the likes. And then also as a third point, to quantify the financial and outcome-based risks associated with the preferred option. And that's really going back to the other commodity price instability and climate change. So yeah, as I said before, the work was initially commissioned by the finance department, but there's also subsequent interest from our politicians in a prudential borrowing approach, which is adopted by Blackpool. So we're now part of this Highways Asset Renewal Partnership that some people may have heard. And certainly there's an innovation forum in there that will be feeding back a lot of what we're doing in Stockport to that. Here's a quick overview of the model. It's not, this isn't a whole architecture within a single software. It's a process. The bit that we're focusing on is down here on estimation of deterioration model parameters. The bits on the right, the option scenario testing and Monte Carlo simulation, those are all within a bespoke model of software that I've developed specifically for this task. So once we've estimated the deterioration model parameters, they then go into they're sort of processed, and we input maintenance budgets in here. So there's a whole set of maintenance decision rules about minimum and maximum time thresholds and life cycle sequencing that we can put in against all these other condition triggers, and we use that stage really to identify a broad preferred options and business as usual scenarios and other options that we might want to look at. Taking that through, then we input that into a Monte Carlo simulation, which is really, it's like sampling, taking a sample of 1,000 possible futures that could happen, given all the uncertainties that we can't quantify exactly what's going to happen with commodity price projections, but we can use the benefit of some history, mean and standard deviations of different commodity prices, construction indices, input those in. Again, climate change projections, haven't got direct evidence as yet as to how various extreme weather events impact on the deterioration models, but certainly we're quite fortunate in Greater Manchester that there's been an Eco-Cities project which has done some localised climate change modelling. So we've got some projections about the likely changes in risk from extreme weather events in Greater Manchester. Well, the next slide will actually just briefly show you what the kind of output would look like. I have cheated with this. This is made up data, completely fabricated, I'm afraid. This is an output from Monte Carlo simulation, effectively. This could be any kind of outcome along the bottom axis there, whether it be benefit cost ratio between the preferred option and a business as usual scenario, or a specified service level, a condition service level. So we'll produce these outputs for each of those kind of parameters. And effectively what we're doing is we're just saying what's the risk. Say what's the risk that we could turn out with a BCR of less than 1, say, or that we don't meet our minimum service level requirements having invested. And then we can also provide this, a 90% or 95% confidence interval on that. And that just gives us more information to support decision making. So just to quickly describe some of the data, unfortunately, obviously because time's limited, I don't want to sort of go into the detail of why we've used certain data sets and not others. You might notice that Scanner is not on there. And I did spend a lot of time looking at Scanner data, but in this instance, really, we decided I just couldn't use it in the deterioration model. The reasons for that would probably be a subject of another presentation, so we'll just have to take that as read at the moment. The carriageway treatment survey is really sort of part of this highway asset renewal partnership setup that we have with really following the model that Blackpool Council used, and this is really a sort of visual survey, walked survey of the whole network. Providing 5 condition bands, but additional information on causal factors as well. So reinstatements again, where we know reinstatements have been a factor in structural failure. That kind of information is in there. GPR, Fugro did a GPR survey of a classified network back in 2010. And at that time, the main reason for doing that was really because we were hoping at some point to have some kind of investment program. we would be able to use that alongside deflectograph, obviously, and, at specific sites to improve our programming, really. As it happened, really, we need this initial investment to be able to do that. So I thought, well, let's use the GPR data actually in the developing the deterioration models as well, so we can actually get the investment model up and running. Also use Scrim. I'll probably describe a little bit about that in a minute when we as we're going along. And maintenance history, which is vital, really. One thing you'll notice, though, is I've only got 1 point of condition data. What I really need is the maintenance history then to be able to infer a deterioration model from that. Because normally you'd expect to have multiple years of condition data to be able to see trends. So I better try and put a photo in there somewhere because it's there'll be a lot of charts around. This is really just to illustrate the problems we've got really with trying to develop an appropriate deterioration model. So we've got a lot of utility openings, patches, ironwork failure, chipping loss, and then further up there's actually some longitudinal cracks there, but they're associated with a hidden trench that's since been obviously resurfaced over and has then emerged as obviously a deeper structural failure. We don't have all the data that we would need to be able to model that in detail. So ultimately, we've got to have a model that can cope with a large amount of variance. And this is really just sort of saying that the deterioration models are probability-based. The model outputs are interpreted at the level of network subgroups. But, as I mentioned earlier, the probabilities could be used in future to set post-treatment time thresholds for resurvey and investigation. So we could produce a long list of potential schemes just by looking at the time elapsed since the last major structural treatments. And this is a schema of the one particular kind of model. We could set this up anyway, really, in the software itself. If we start off with a new surface, these aren't in physically mutually exclusive condition states, but some surfaces may experience then early life skid resistance loss, whereas others won't. Ultimately, they'll go to structural impairment, at which point, from a budgeting point of view, the structural impairment is the key issue. Obviously, as a prioritisation, the skid resistance loss is still an issue, but that's more for a kind of tactical programming level. So this is really, effectively, we're interested in where skid resistance loss has occurred before structural impairments as well. The horrible little expressions here, this is the only way I could succinctly put it without filling up the page. What that means is that the time elapsed between one condition state to another is unknown, basically, but it's distributed according to a particular probability function. And so the task of deterioration modelling is to estimate these parameters in whatever model form they might be. This is some data that I've collated using the Cadway treatment survey data and maintenance history. So each of these bars is basically representing a cohort of schemes that were done, say on the right-hand side back 16 years ago. It's just a sample, but you can obviously see then, because they're obviously separate samples, they go up and down. There's a bit of random data noise in there. But ultimately, you can start to see the trend in there. One of the key issues, though, there are two major issues, really. So actually, I didn't explain this properly. What this is showing is basically the proportion of all those roads treated 8 years ago, say, that have now gone into red condition. Red meaning structural failure, effectively. So by year 16, we've got an age cohort there where over 50% of it has gone into had structural failure. The key issue from these two major points really to take from this is obviously the amount of variance in failure time. Some of these earlier failures may well be down to reinstatements, but ultimately that's life. We've got to incorporate that into our investment model if that's how it happens. And ultimately, reinstatements, from our perspective, are an external, effectively a random occurrence, particularly if they're emergency reinstatements. So they have a place in a random probability model. The other issue, though, is that even if we were looking at just mean times to failure, we haven't got the full picture here. We haven't got data stretching back 30 years or whatever, which means we can't actually calculate through a basic process, so we can't calculate the mean time to failure. So we need some kind of theoretical model to fit to this. And this is it. Well, this is it for this was really my saviour anyway with limited data. All this is don't really need to go into much of the detail. This is called the viable distribution. It's used quite a lot in reliability engineering, and it's got a particular theoretical basis for systems where a failure could come about through multiple different causes. And ultimately, the task here, what this is saying is the probability of the time of transition or failure or whatever being less than or equal to a given time. It just follows this formula here. So it's a function of time post major structural treatment. And the task is basically to estimate these two parameters given the data. And the next slide just sort of illustrates what these two parameters do. So that alpha parameter sort of slides it off to the right. The smaller the alpha, the bigger the alpha gets, the further to the right. So it means there's a tendency to last longer. And the beta parameter just deals with the variance effectively. So it stretches or squashes it. And I just showed this again because this will just help a little bit with the interpretation of subsequent slides. This is just exactly the same models, but in a cumulative probability. So you can see probability up on the right, up on the left there, sorry, going up to 100%. And this is a model fitted to the same data that I showed you a bit earlier on. This is for all our classified road network, effectively. So it's a fairly broad classification because we haven't got an enormous sample to work with. But that then gives me something to work with when I'm developing the deterioration models. I can also then look at what's going on beyond that 16-year period. Sense checking, just really important. Obviously, I could sit here and do all the statistical modelling, but ultimately we need to sit down and look at what the implications are. Using that model, you can derive a median failure time from that directly. It's fairly straightforward, and you don't need to worry about the maths there. In the example before, that gave a median failure time of 17 years or so, which is actually a bit shorter than the default failure time or useful life that CITFA have put in their whole of government accounts records. Mean time to failure can also be calculated, but it's a horrible looking equation. I didn't think I'd put it on here, but you can just input it in Excel and calculate it pretty quickly from those parameters. And as I just implied there, we can then use that for the whole of government accounts. That's sort of valuation process to produce our annualized depreciation value. But that's a separate process, really. That's something that we'll look at doing afterwards once we've done the main model work. Here's some more examples of other. Don't need to go into too much detail, but here's a couple of things you might be able to look at afterwards. Some other parameters I've estimated for other parts of the network and for different condition levels as well. So post-preventative on the strategic, I've also got then the time to that structural failure, and we use red to indicate structural failure. So post-preventative treatments, I've got then 13 years, 11 and a half years as a median time to transition. I haven't got any data from the unclassified network at the moment because I'm still trying to ratify that with the engineers. And I'm running low on time, I think, but here, this is really just to show how I then use these cumulative curves to derive a multi-stage deterioration model, because ultimately what I'm talking about at the moment is just a two-way, a binary process for each different condition type. I'm talking about from new to whatever that condition band is, or worse. And so what I do is I effectively stack them all up together. So these lines here are actually lines that they represent a cumulative distribution of all the roads that go into that have a sideways force coefficient less than 0.45 and worse. So it's basically a cumulative chart. It means then that I can estimate from this, it's not an ideal process, but taking the difference between that and the other condition band curves, that's effectively the difference. That's all of the rows that are in that particular condition band. How I actually work out what the dwell times are in that particular condition, and what rate they all then go into red afterwards, is we need to make a few assumptions about correlation between them. Issues I wanted to just mention was the potential bias that comes from using samples of recent maintenance schemes, because faster deteriorating roads will tend to self-select in the sample. There's a kind of parallel with speed surveys that faster drivers tend to be overrepresented in the sample. This is really just to explain one of the particular kinds of model that I've used to actually incorporate some variables in. The important thing here is that this requires a basic assumption that the relative failure probability of one type of road against another, which is the odds ratio, remains constant throughout time. So regardless of what the deterioration curve is, that sort of relationship between them remains constant. And that enables the separate estimation. You can actually do that as a separate process. Effectively what I'm doing is estimating parameters within this model, which they're like a suffix to the main deterioration model. So that deterioration model, the precise form of that isn't required to be able to do this estimation, which is very useful when you've got limited samples. So this is just an example of some parameters that I've estimated. If the parameter is positive, it means it has a knock-on impact. It increases the deterioration rate. So here, what I've used is GPR data on bituminous layer depth. The areas where we've got bituminous layer depth less than 300 mils. This is like a binary indicator. Obviously, that then has an effect on increasing the deterioration rates, and so I can input that into the model to produce a separate curve. Conversely, where I've seen the GPRs come up with a particular reading for a sub-base, then I've used that. It's really the best indicator I've got at the moment. But that also then has a positive impact in reducing deterioration. And I think probably rather than go through any of the other ones, I'll just show you some of the effects of those. That's the same. That's applying that parameter that I showed you just previously to bituminous layer depth. So you can see the dashed line underneath. That's showing the effects. This is actually it's an upside down deterioration curve. So if you're looking at the ones I was showing you before, it's just basically a mirror image. So this is actually called a reliability curve or a survival curve. I was quite surprised there wasn't a more marked impact from areas where we managed to get some information on the subbase. But I guess probably digging into the data more in future will probably yield some more significant relationships. This one was actually looking at material type, and this is looking at the stonemastic asphalt sites that we've got. We've got quite a large number of them around the borough, and it fits quite well with our own anecdotal evidence that a lot of them haven't survived very well. It certainly, colleagues' eyes lit up when they saw this. So that was quite, it's obviously because we've got quite a lot of stonemastic asphalt still under 10 years old, we need to account for that in our deterioration models. So this is probably a reasonable start on that. Future development of the model. this is not, I'm not sort of claiming this is some research output. It's really just a very sort of messy start using the data that we have. What I hope is that we can integrate this into or embed it into our asset management planning, and that we review the data on a regular basis, review the models on a regular basis, and in particular, I think the Cox proportional hazards model, which I just described earlier, it might be very useful to explore the impacts of climate change on deterioration rates. Going forward as well, Bayesian methods, which are a sort of way of formalising our updating of models. It's a very, very strong technique. In fact, it's really perfect for this kind of thing. Really look to use Bayesian methods to look at developing models for introducing climatic events into models. To conclude, too early to report decisions made on the basis of the model. I apologise for that. We'll be actually reporting on this to our council's executive in the autumn, by which time we'll have done all the work, hopefully, so we can we'll feed back the outcomes from that probably through the Highways Asset Renewal Partnership. However, at the moment, obviously, just from the methods I've shown, we are able to produce some sound probability-based models that can be developed for urban networks, particularly, that are subject to highly variable random factors affecting deterioration. Thank you for listening.